Welcome back to the lecture on linear algebra through geometry. Um, in the last couple of lectures, we looked at what are the conditions for the right hand side vector b to satisfy in order to say that the system of equation Ax is equal to b has a unique solution or infinitely many solutions. That means, what is it to say the system is consistent, and we figured out a condition for that. We said that for b to be for any system of equation to have solution, we said that the right hand side vector dot product with the solution corresponding to A transpose y is equal to 0 should be equal to 0. So, if that is the case, then you will have solutions to Ax is equal to b. The problem was when Ax equal to b does not have a solution, and we interpreted that as b not being in the column space of the matrix A. If that is the case, straight away we can say that there is no solution, but then the problem is, like, you cannot leave saying that there is no solution. So, what we do, we were trying to find out some kind of an approximate solution in the sense we wanted to find out a representative of this b vector in the column space of A, and then say for this representative of b in the column space of A, we could find a solution which is, let us say, x dagger. That is what we did in the last class, and we found that the best approximate or the best representative in fact of the b vector onto the column space of A is nothing but the orthogonal projection of the vector b onto the column space of A, and the moment the vector b is projected to the column space of A, onto the column space of A, you can always find out the scalars x1, x2, xn, or let us say x1 dagger star x2 dagger. We basically find the vector x dagger such that Ax dagger is equal to the representative of b onto the column space of A, and we figured out that if the matrix A is a full rank matrix, that means if all the columns of the matrix A are linearly independent, then we could get this x dagger to be A transpose A the whole inverse A transpose B, and we call this A transpose A the whole inverse into A transpose as the pseudo inverse of the matrix A. And therefore, we also said we are not trying to solve, though we wanted to look at Ax equal to b and we want to solve Ax equal to b, there was no solution that was existing for Ax equal to b. Therefore, what we did is we were trying to solve a problem which is Ax star is equal to the projection of b onto the column space of A. That means the problem itself is now looking at a solution to Ax star is equal to projection of b onto the column space of A, and we proved that Ax dagger is equal to A into A transpose A the whole inverse into A transpose into b. We said that the effect of applying the transformation that you have, which is basically A into A transpose A the whole inverse A transpose, the transformation is basically a projection transformation which projects the vector b onto the column space of A. That is what we had. Then we had a few questions. What were the questions that we had? We said, how do we prove that A into A transpose A the whole inverse into A transpose is actually a projection matrix? Then we went to even a more fundamental question where we asked, what is a projection matrix? And then we asked, what are the properties of a projection matrix? And in this lecture we are going to look at these ideas of projection matrices and properties of projection matrices, and we will indeed prove that A into A transpose A the whole inverse A transpose is actually a projection matrix. So, let us get on with the lecture. Okay. So, the question is, projection. So, we are going to look at projection matrices. First of all, let us try to understand what projection means. What is it to say projection? Say for example, I have in 2 dimension, I have let us say this coordinate axis x1 x2 and I have this vector which is say u. Now what is it to say projecting u onto the x1 axis? It's basically okay, it's basically saying that okay, I just I just hit this vector on the head so that it falls down, and what is the point at which it falls down on x1? That corresponds to the projection of u onto x1, basically the shadow of u along the direction of x1. Similarly, what is it to say projection along x2 axis? Basically you try to hit this vector this way, you try to find out the shadow of this vector u along the direction of x2, that is what projection means. Now the moment you apply projection here, that means this fellow has fallen. If you try to apply another projection, what happens? That fellow is just going to go in the same direction, is that right? It is not going to change. So that is something which we need to understand. So what we say is we are going to look at definition of a projection matrix. So let us look at this. P is said to be a projection matrix. P is called a projection matrix if and only if A P transpose is equal to P. Now what does that mean? P transpose is equal to P implies that P is a symmetric matrix. The second part is P squared is equal to P, and this property, we call this property as idempotent property. We call this as the idempotent property of the projection matrices. Now let us look at the proof. Right, let us look at the proof. This is basically a definition, and it also it's called the theorem. It's actually a theorem where we say that matrix P is projection matrix if and only if P transpose is P and P squared is equal to P. Right. So let us look at this. Suppose P is a projection matrix. That means P satisfies this properties. Suppose P is a projection matrix satisfying P transpose is equal to P and P square is equal to P. It is a projection matrix, means it basically says this P square is equal to P. Or let us say okay, let us say suppose P is a matrix, let us say why should we take it as projection matrix? We will just take it as any matrix. P is any matrix which satisfies this, then we need to prove that P is a projection matrix. So if this is the case, what we need to prove? We need to prove that B minus projection of any vector, let us say B, PB is orthogonal to the column space of P for all B, right. That is what we need to prove. Okay. So let us look at this. So any vector in the column space of P, any vector in the column space of P is of the form let us say Pu for let us say for all u, okay. So what we have? We have Pu dot B minus Pb is equal to, what is that? This is basically saying U transpose P transpose into B minus Pb. This is what it boils down to. Pu the whole transpose into B minus Pb. So what we have is U transpose P transpose into B minus Pb. Now what we have? We have U transpose into P transpose B minus P transpose Pb. This is what we have, right? If you expand this, we have U transpose into P transpose B minus P transpose Pb. But we know that P transpose is equal to P and P transpose P is equal to P into P is equal to P squared, which is equal to P, because those are the two properties that the matrix P satisfies. We want to establish that P matrix is actually a projection matrix, right? We have taken P to be any matrix with this property, P squared is equal to P and P transpose is equal to P. We want to establish that the matrix P is actually a projection matrix. So we have this. So what do we have? This implies, let us take this as 1. Therefore this implies 1 is equal to U transpose into P transpose P, B becomes Pb minus P transpose Pb is P square B, which is the same as Pb. So what do we get? We get U transpose into 0, which is basically 0, right. That means what did we do? If the matrix P is a projection matrix, then we wanted to prove that the B minus projection of B onto the column space of T is basically orthogonal to the column space of T, and that is exactly what we have proved, because this Pu corresponds to a vector in the column space of T. This is basically the orthogonal projection of B onto the column space of T. So we have proved that this is done. Now let us look at the converse. Conversely, what do we have? Suppose if P is projection matrix, then we need to prove this P square is equal to P and P transpose is P. Suppose P is projection matrix. Right? We have, because we have already told this P is a projection matrix, we have B minus the projection of B onto the column space of B is orthogonal to the column space of P. So we will say it is orthogonal to Pu, yeah, where U is any vector. That means we have 0 is equal to Pu dot B minus Pb. This is what we have, which is nothing but Pu the whole transpose dot B minus Pb. That means we have U transpose P transpose into B minus Pb. This is equal to 0. Yeah, which is nothing but U transpose into P transpose B minus P transpose Pb is what we have, right, which is nothing but 0 is equal to U dot P transpose B minus P transpose Pb is equal to 0, right. Now U is basically all vectors that you have. You basically look at all the vectors in Rn, that is exactly what we had, right. You had Ax equal B, you look for x in Rn. So U is basically the set of all possible vectors that you have, and you want the dot product to be 0. The only vector which is orthogonal to all possible U vectors is basically the 0 vector, right. So the only vector, uh, orthogonal to all the U vectors, all the vectors U is the 0 vector. Which implies P transpose B minus P transpose PB is equal to the 0 vector that we have, which implies P transpose P is equal to P transpose PB. This is what we have, right. Now on both the sides we have B, on one side, left hand side you have B is basically pre multiplied by P transpose, on the other right hand side we have the B vector to be pre multiplied by P transpose P. This implies P transpose is equal to P transpose P, right. P transpose is equal to P transpose P. Now what we do is, we already had seen in the previous case where we took a matrix A, m by n matrix, and we took A transpose A, that basically gave me a symmetric matrix and a square matrix. It is a symmetric and square matrix, which means we have, what is that we have, P transpose P is basically, okay, we know that, so we know that P transpose P is symmetric. Now here we have a matrix P transpose which is equal to a symmetric matrix, therefore we know, therefore P transpose is symmetric. Which implies P transpose is equal to P. And the moment we know that P transpose is equal to P, we this also implies we have P is equal to P transpose P is equal to P into P, which is basically P square, right. So we have P transpose P is equal to P into P, which is P square, and that is equal to P, therefore we have, which implies P square is equal to P. So thus we proved that any matrix P is called as a projection matrix if the matrix is symmetric and if the matrix is idempotent, that means P square is equal to P. Okay. Now let us look at a simple interesting stuff where I want to look at how do I get, given a vector, how do I get a matrix which is a matrix which helps us project a given vector onto, let us say, another vector, right. We want to look at that. So given vectors, let us say u and v, what is the matrix that projects the vector u onto the direction of v? So that is a question that we have. can we find a matrix which will project any vector u in the direction of v? How do we find that out? We know that projection of u onto v is basically given by u dot v divided by v dot v, of course you have in the direction of u, in the direction of v. We wanted to project v in the direction of u, so we say in the direction of v, right. Therefore, this basically is the scalar that we have, which is basically say some Tv. This is what we have, right. Now let us look at this. We have okay, let's look at this. So what we have? We have u dot v, so projection of u onto v is basically v transpose u divided by v transpose v in the direction of v. Yeah, this is what we have. Now this is a scalar and that is a vector, that v is basic, this is a vector and that is a scalar. Now what I do, I want to put this, it is like saying 5x, I will say x into 5, I can write this as 5 into x. So what I do is, I basically bring this v here, so I get v transpose u divided by v transpose v, which is basically v transpose divided by v transpose v into u. Let us look at what is v transpose. We know that v transpose v is a scalar. V transpose v is the dot product of v with v, dot product of v with itself, and it is a scalar. Let us look at what is v transpose. v transpose is not equal to v transpose v, because if you look at the operation itself you can actually find out that they are different. So what is v transpose? Let us assume this vector v. So let this vector v have components, let us say v1, v2, v3. Now what do we want to find out? We want to find out v transpose, which is basically v1, v2, v3 into v1, v2, v3. Now if you had seen in the first couple of lectures of this course where we dealt with the idea of matrix multiplication, you can multiply two matrices provided the number of columns in one is equal to the number of rows in the other. You had m cross n, you can multiply this m by n matrix with another n by m matrix. You can't multiply an m by n matrix with another m by n matrix, you can only multiply an m by n matrix with n by m matrix, right. So in this case we have this vector v, it is a 3 component vector, 3 by 1 matrix, and v transpose is basically 1 by 3. So I can actually get, I can multiply these two matrices, and what will I get? I multiply a 3 by 1 matrix with a 1 by 3 matrix, I am going to get a 3 by 3 matrix here. So I am going to have a 3 by 3 matrix. So v transpose basically results in a matrix, whereas v transpose v results in a scalar. So let us look at what is this. So this is nothing but it is basically scalar multiplying this v1, v2, v3, that vector with v1, v2 and v3 separately. So I am going to have v1 into v1, v2, v3. The second column is v2 into, the second column is v2 into v1, v2, v3, and the third column is v3 into v1, v2, v3. There is something interesting. If you look at all the 3 columns of this matrix, there is only one column of the matrix that you have which is linearly independent, all the other two columns are basically multiples of, all the three columns are basically multiples of each other. That means I just have one linearly independent vector here. Therefore the rank of this matrix, so look at this is basically a 3 by 3 matrix. We are going to write this, rank of VV transpose of the matrix VV transpose is always 1, and this is basically what we call as the outer product of two vectors. Outer product of two vectors. The inner product of two vectors gives me a scalar, the outer product of two vectors give me a matrix, and what is interesting is the rank of the matrix is 1. Is that clear? So outer product of two vectors always results in a matrix of rank 1. Right, it always results in a matrix of rank 1, especially I will say okay, it results in rank 1. Now what we do is let's extrapolate, let's do a little bit more here. So the first point, VV transpose is a rank 1 n by n matrix. Let us look at what kind of n by n matrix is this. So what are we going to get? This matrix is basically equal to V1 square, V1 V2, V1 V3, V1 V2, V2 square, V2 V3, V1 V3, V2 V3, V3 square. That is interesting. VV transpose, the outer product of a vector with itself, results in a symmetric matrix, symmetric rank 1 matrix. So VV transpose results in rank 1 n by n symmetric matrix. Second, so of course we will okay, the second, UV transpose, if U and V are of different dimension, if U and V are of different dimensions, then UV transpose results in an m by n matrix of rank 1. For example, let us take this. Suppose if U was U1, U2 and V was basically V1, V2, V3. So what we want? We want U V transpose, which is U1, U2 into V1, V2, V3. So what do we get? We get V1 into U1, U2, V2 into U1, U2, V3 into U1, U2. This is again, the columns are all scalar multiples of the same vector, so it is going to be a rank 1 matrix, but of dimension 2 by 3. So UV transpose in this case is basically a 2 by 3 matrix of rank 1. Is that okay? So that is what we have. So what are we trying to say? So if we have, So therefore the projection matrix, so the matrix that projects any vector onto the direction of let us say a vector v is given by P is equal to V transpose divided by V transpose V. Now we have a question, does P satisfy the properties of those projection matrix? P square is equal to P and P transpose is P. Let us look at what is P transpose. Now P transpose is 1 by V transpose V, this is just a number, into V transpose the whole transpose, which is nothing but 1 by V transpose V into V transpose the whole transpose into V transpose, which is nothing but 1 by V transpose V into V transpose. That means P transpose is equal to P. That is interesting. Let us look at if P square is P. What is P square? P square is V transpose divided by V transpose V into V transpose divided by V transpose V. Now what is it that we get? We get V into V transpose V into V transpose divided by V transpose V into V transpose V. Now this is a scalar, that means I can pull that out and then put ahead, so I can cancel this guy with this guy. So what do I get? I get V transpose divided by V transpose V, which is P itself. Wow, that is interesting. Now suppose we want to look at, let's look at this. Suppose we want to project a vector we want to project a vector onto a plane spanned by orthogonal vectors, spanned by two orthogonal vectors, let us say u and v. That means we say that u dot v is equal to 0. This is what we have. I want to find out the projection matrix. So what is the projection matrix that, so the projection matrix, how do we find the projection matrix? That is easy to do. It is the same thing. Now you have orthogonal vectors. So what you can do is, suppose I have let us say I want to project a vector, project x onto the plane spanned by u and v, and u is orthogonal to v. How do I do this? So projection of x is nothing but, let me write this, so projection of x onto the plane spanned by u comma v is given by, we already know what is it for the single vector, right. So I have u transpose divided by u transpose u plus v transpose divided by v transpose v x. That is all it is, right. So the question is, check if u transpose divided by u transpose u plus v transpose divided by v transpose v is symmetric and idempotent. Now let us get back to the same question that we had. We wanted to check whether that A into A transpose A the whole inverse into A transpose B, if that is going to be a projection matrix or not. We want to check that out. Let us do it. Recall, we said Ax dagger is equal to A into A transpose A the whole inverse A transpose B, and we called this as the projection matrix. Projection matrix. So let us actually prove if that is projection matrix. So what is projection matrix? P transpose is equal to P square, P transpose is equal to P symmetric, right. Let us check this. A into A transpose A the whole inverse into A transpose, take the whole transpose of this. What is that? That is nothing but A transpose the whole transpose, A transpose A the whole inverse the whole transpose into A transpose. Now A transpose A is a symmetric matrix, A transpose A inverse is a symmetric matrix, therefore A transpose A the whole inverse is A transpose A, and this is going to be A transpose transpose, which is actually A. So you are going to get A into A transpose A the whole inverse into A transpose, which means we have proved that this matrix is actually symmetric matrix. Let us look at P square is equal to P, let us see if that holds good. A into A transpose A the whole inverse into A transpose into A transpose A the whole inverse into A transpose. Now if you look at this carefully, you will see that these two products are basically A transpose A the whole inverse into A transpose A. It is equivalent to saying I have the matrix B into the matrix B inverse into B, that is going to be identity matrix. So this is going to be what we are going to get. We are going to get A into identity matrix into A transpose A the whole inverse A transpose, which is the same as A into A transpose A the whole inverse A transpose. Therefore this matrix A into A transpose A the whole inverse into A transpose is a projection matrix indeed. Right? Great. Okay. So in this lecture what we looked at is we basically looked at the idea of the definition of projection matrix. Basically we looked at a theorem which said the matrix, any matrix P is said to be a projection matrix if it is symmetric and idempotent, and we proved that also. And then we went on to ask this question like what is the matrix that will project a vector onto another vector. We know that we could do it the dot product way, but we wanted to find out a matrix which is going to project a vector onto another vector, and we figured out that this matrix turned out to be the outer product of a vector with itself divided by the dot product of the vector with itself. So we had V transpose divided by V transpose V, and then we looked at what is the matrix that projects any vector onto a plane which is spanned by two orthogonal vectors. We said that it is the sum of individual projection matrices, and then we also proved this matrix which we had where we projected a vector which was out of the column space of A, the matrix A, we projected that onto the column space of A. That matrix which we had, which is A into A transpose A the whole inverse into A transpose, we proved that is also a projection matrix. In the next lecture what we are going to do is we will be looking at the properties of pseudo inverse. The pseudo inverse is something which is very interesting. We will look at certain properties of pseudo inverse matrix, and towards the end of this module we will also look at the pseudo inverses, the pseudo inverse of some special matrices, and we will then get onto a journey of our linear algebra course into real symmetric matrices, where we will again do the idea of eigenvalues and eigenvectors. We will look at eigenvalues and eigenvectors, and we will look at real symmetric matrices, eigenvalues, eigenvectors associated with real symmetric matrices. Then we will look at the idea of eigen decomposition as far as eigenvalue, I mean the real symmetric matrices are concerned, and then go ahead with quadratic forms. So that will be the agenda for the next couple of lectures and modules. Namaste.